Okay. So it sounds like a lot of people, I've been to a lot of the sessions here, everybody, gives the Kubernetes 101. I'm not going to do that today. I'm going to try to, there are a lot of things about big data workloads that are very different than the traditional workloads that are running on Kubernetes. I'm going to do a demo, but at the same time, I'm going to try to explain a lot of the pain points you'll run into and some of the techniques for working around those. I'm Sky or Skylar. I'm really excited to talk to you today. Things are changing very, very rapidly in how easy it is to push these environments out into the real world today. I'm going to talk at the beginning a little bit about some of the problems I had a couple of years ago, why they're different now, the different weapons that you can use in Kubernetes to help you win your street fight, techniques you can use to do data science at scale. I'll be demoing building a data science environment throughout this presentation. I'm just really trying to get you to understand the basic pattern of these environments, because there are very basic patterns. No matter whether we're doing PyTorch or TensorFlow or Spark or some Hadoop, there are certain ways you want to build these environments, and there are certain things you always want to do, and there are certain ways you want to treat Kubernetes. So I wanted to start off and talk a little, this is really personal to me. A few years ago, I lost my little sister to heart disease and medical mistakes, and I decided to build a startup. And I wanted to take fitness tracker data, combine that with deep learning, and see if there was any correlation between your heart rate on your Basis watch or your Apple Watch today, or your Fitbit, how much you're walking, and whether that could tell us anything about your body and your health. Could we create a check engine light that says, hey, you should probably go see your doctor? Started to think about it. It looked like with all of the advances in deep learning that were going on at the time, it looked like the perfect time to do something like that. And so I started trying to build environments to experiment and play around with things. And this was around 2013. Hadoop was still a really huge deal. Docker was just appearing on the scene. Spark was young, moving fast. TensorFlow was totally brand new. I think I started doing a lot of this right after the TensorFlow announcement. Hinton's ImageNet results were out there and lots of recent papers. And it seemed like the perfect time to experiment, but it was a nightmare. I banged my head into wall after wall after wall after wall. And I think that's not going to be the case today, but the big issues that I ran into at the time were no great notebooks for data exploration. Notebook frameworks at the time were kind of finicky. Lots of Python version woes. Each framework was complex to install, get running. MapReduce, Mahout, Spark, TensorFlow, Torch. Ability to experiment was limited and deeply discouraging. I was forced to own both complex environmental engineering and data science. That's something you definitely don't want to do. You want to play on one side or the other. It's hard to do both. 2015 to 17 got a lot better. Exploration on a single machine was pretty good. Notebook technologies got better. TensorFlow got much better. Creating training jobs under TensorFlow was simpler. Spark grew to 2.0, lots of new features. Still limited by Yarn at the time. Many components became containerized, but orchestration was still a challenge. Today, we're at a point where containers are ubiquitous. Kubernetes is insanely powerful at orchestrating things. Spark has native support for Kubernetes. Kubeflow is beginning to make deployment of ML environments in Kubernetes simple. And in summary, things are now orders of magnitude nicer for an IT department wanting to support a company's data scientists. So how do we do this? So there are three main steps. You got to procure an environment. In many organizations, you'll have one huge Uber environment with tons and tons of machines. It'll be on premises, could be in cloud. Doesn't really matter where their environment is anymore. If you're running Kubernetes, the challenges on AWS versus GCE versus an OpenShift cluster that you built on premises, all of these things are very, very similar. All we need is really a set of machines with Kubernetes installed. In the cloud, it can take minutes to procure. On premises, it could take you months to get the PRs approved. But I'm going to, I've already procured an environment. I'm not trusting the demo gods today to create 50 cloud servers. If we look, let's see. Okay. If we look real quick in the development environment, I did run it. I ran it this morning. It took about 4 minutes and 14 seconds to procure about 50 servers. If I look out at Google right now, it's this GCE cluster. I've got about 800 virtual CPUs. I've got 5,200 gigabytes of RAM. Decent sized cluster. These clusters build, you don't want to scale Kubernetes past a couple of thousand nodes, but building 1,000 nodes takes about the same amount of time as 50 nodes. It just depends on the cloud vendor and his environment. Nothing really special here about machine learning. Going back to the slides. So I already did that, but I want to first create some storage. Now, I work for a storage company. I'll talk a little bit about why storage is so important to these environments, but I'm not gonna focus on that, but I am installing our MapR storage CSI and storage environment inside of Kubernetes. So if I go to here, I've already procured the nodes. Right here, I'm just gonna tell it to go ahead. Oh, before I do that, I'll show you the 50 node environment. Let's see here, let's go to pods. Actually, this little tool is a little bit shy when I don't use kubectl in a while. So I'll just kubectl get pods. So hopefully I'll connect to my Kubernetes environment in a second. Okay, so this should be a little bit. So right now you can see I just have 3 namespaces, the default, kubesystem, and kubepublic. If I go out and go ahead and tell it to install the MapR components in the environment, all my storage is getting installed right now. And if we look, I got 2 new namespaces, a namespace for the CSI components and a place to put my operators. So I'm going to be installing a lot of this stuff via custom operators today. Anybody familiar with building operators or using? We'll talk about operators as we go along in the presentation today. But these are operators that I send it a bit of YAML and it builds out a really complex storage environment, storage cluster. So I have the operators installed. Let's see. Oh, kubectl apply -f. So this is my custom resource for my MapR cluster that's going to spawn off all of the storage. So if I go and look now in the environment, it started creating this full example cluster and an LDAP namespace. If I go into full example, it's creating hundreds and hundreds of pods now. We're creating storage on every node in the cluster. There are daemon sets, there are stateful sets, there's zookeeper. There's lots of different things, but I'm not going to talk about that today. The final thing I want to do before I continue with talking about things is I'm going to install Kubeflow. How many people have used Kubeflow in Kubernetes? If you haven't, it's a really cool set of technologies. So it bundles up a lot of machine learning technologies like TensorFlow, like PyTorch. It creates UIs, et cetera. We'll talk about them in the presentation as we go along. But Kubeflow is actually where the real machine learning stuff happens. I'm going to install the Kubeflow components in its own Kubeflow namespace. Now, when I create jobs, I'm going to be creating them in in user namespaces. But let's go ahead and install Kubeflow. So that's going to start up, and I'm going to let that run. All of this takes a couple of minutes to install, not a long time at all. But I'm going to go back to the presentation for a minute. And so we've created storage. We did that. We created the data science environments. We created Jupyter Hub, TensorFlow, Argo, Seldon Core. We'll talk about those as we go along. So Kubernetes is up. It's got our components in it. Kubernetes is really great. We can run warehouses full of workloads, and everything's wonderful. Kubernetes has this notion of pets versus cattle as a deployment model. Before Kubernetes, the idea was that we had these really important servers that we babied. We kept the OSs in tip-top shape. We got our VMs working well. And Kubernetes kind of turned that on the head and said, let's not care about these. They're just a bunch of boxes. Let's number them and brand them. If something dies, we'll just get rid of it and throw it away. And that works really well for certain types of apps. The problem is state. The traditional problem with these types of environments is I need to store data. And in the Kubernetes world, Kubernetes by default, if you're not using a stateful set or a daemon set, Kubernetes doesn't care where your pod runs. It's gonna stop that pod, move it somewhere else, and continue on. But data science workloads don't work that way. They're the worst consumers of stateless data that possibly could exist. They need massive amounts of training data. You need to create models. You have shared notebooks. All of these things are very hard in the traditional Kubernetes environment, but we shouldn't give up. Kubernetes has rapidly gotten support for stateful applications built in. There are still some things that would be really helpful if they'd get out of beta, but the main components that Kubernetes now has to help us handle this, excuse me, smoke. Stateful sets, daemon sets, persistent volumes, persistent volume claims, the new CSI driver for storage, and all of that has made Kubernetes a much nicer environment. So the rest of this presentation is really about what are the problems and what do we get out of Kubernetes and how do we use it to its biggest advantage. So Kubernetes is all about pods. Pods are the unit of management in Kubernetes. Pods get spread around on all of these nodes. How do pods help us in building real-world data science environments? Well, it's critical to understand the nature of work for data scientists. They're called scientists for a reason. They do novel things. One of the problems that people traditionally have with data science environments is that data scientists want to put whatever they want on the machines. They do not want some cookie cutter website that corporate approves. They want to use the tool that they're most familiar with or most comfortable with or is the most appropriate tool for the job. And that's traditionally very hard for IT to deal with. Pods and their levels of isolation help us. Now, pods aren't perfect. Pods are not virtual machines. Pods, if users can put whatever they want in a container and they're running along with the accounting software at the same time, that can be a problem. Better pod isolation, the gvisor project that was just announced, these are things that are very important to think about when you're building these environments. If you're gonna let data scientists be data scientists, and you really need to, you also need to think about isolation from other users. You can use taints and tolerations as another kind of stopgap until you have more true isolation. So Kubernetes namespaces and resource quotas. So the other thing that's really typically hard in data science environments before Kubernetes is the idea that we have training jobs that can last months. We have many different data scientists that are trying all kinds of different things. Kubernetes has namespaces and resource quotas to help you keep users from taking over resources from each other. And you really need to pay a lot of attention to how you're setting up the namespaces, what tenants have what resources. All of this is really critical because most, if you go out and you start downloading pods or start playing around with any software that's designed for Kubernetes today, people do a very poor job about isolating it, setting RBAC rules, et cetera. This is one of your primary tasks as someone that's managing this infrastructure. You have to think about this very, very carefully. You want to figure out how you want to divide your projects and tenants, how you want to budget resources for them, how you want to give them specific namespaces. You want to specify as many resource quotas as you can, because if it can be taken away from other users, it will be taken away from other users. So don't just think about CPU and memory. That's a good start, but ephemeral storage, local storage, extended resources and GPUs are absolutely critical for a lot of these workloads. So figuring out what departments and what namespaces have access to those resources and what that overall pool is, how you allocate or over-allocate those are all critical questions that you need to think about. But Kubernetes does have the tools to help you do that. Persistent volumes, persistent volume claims, and CSI drivers. So the main thing to point out here is that most of if you're coming from the big data world in Hadoop, most of Hadoop is based on this notion of HDFS. My company ships an HDFS implementation, but in the machine learning world, most of the accesses are POSIX. And so if you're going to be running TensorFlow, if you're going to be running PyTorch, if you're going to be running a lot of these types of workloads, you need a POSIX driver that's integrated into Kubernetes. You have to figure out which one you want. And CSI is the latest and greatest standard for that. It just actually got to 1.0 last week. The problem is it's 1.0 for Kubernetes 1.13. So we've still got about a month of slack till CSI. But that's really great news for statefulness. You need to move state out of pods. Now, you don't have to write to persistent volumes and therefore through the CSI layer. You can call out to a stream via Kafka. You can talk to a database. You can talk to an S3 type of API, NFS. All of these are options, but it's really critical for a lot of these applications to talk POSIX. So weapon number 3 is Kubernetes-aware storage. I kind of took a little of the thunder on the last slide. The one point I wanted to make here is copying data sucks. This is the only plug for MapR in this. That's one of the hardest things to do is if I'm spinning up a bunch of TensorFlow job with a bunch of workers, and each of those workers needs to be talking to huge amounts of training data. Right now, if you don't have some sort of storage solution that's moving the data across the entire environment, what you have to do is copy files. That takes a long time. It consumes a huge amount of storage. So that's something you really want to think about. Read-write access to your data sets is a requirement, even if you must copy. So it's not enough to have just a read-only copy of the data somewhere that's 3,000 miles away. Almost always you'll have to put it really close to the containers themselves. Data security and isolation at the user, team, and application levels is big. So you're going to have a lot of data scientists dealing with a lot of privacy-sensitive information. How you store that and where you store that and what your storage does about isolating it is a big deal that you need to think about. But it is very solvable now. Okay, so so we created all of that stuff. Let's get out of the slideshow for a minute and just make sure everything went okay. So we've got a bunch of storage pods that are up and healthy. We've got Kubeflow, a bunch of Kubeflow pods that are up. So everything looks like it's running okay there. I'm going to go ahead and start out some processes so that we can show that we can connect to Kubeflow. If I go over, and this should be the main dashboard for Kubeflow. The main components that I'm going to show off today are Jupyter Hub for notebooks and the job dashboard for TensorFlow jobs. So right now I don't have any jobs to show. Let's see, if I go back, I'm going to start a notebook up. So what I'm doing here is, and I'll talk about this in just a minute, a lot of data scientists live in their notebooks. And so one of the problems that you always have is they've got to spawn notebooks. And notebooks are containers. So they're spawning their own containers. You've got to have some user interface to go in and say, hey, where's the Docker image that I want to launch that contains my notebook, and start it up. That's what Jupyter Hub does here in this case. But I'm going to go ahead and spawn a Jupyter Hub instance. It may take a little bit, so I'm going to go back to my slides. So, so data science patterns. So basically what we're doing most of the time is we're exploring data, we're training data, or we're deploying our models. There's data cleanup, there are all kinds of other pre-stages, and you could divide these stages up in different ways. But you're really thinking about these three things. And the one that you're probably most concerned about when you're scaling this stuff up is the training side of things. So I'm going to start in the middle, and I'll go back to the notebooks and talk about that. But basically, the idea is you need to train in lots of different ways. There are a lot of Spark users in this audience. You can run Spark-on-Kubernetes now. You can run TensorFlow. All of these follow a single basic pattern. It's very important to understand what that pattern is. They use an operator. I'm going to do a slight digression. What is an operator? An operator are just a pattern. They're not anything. They're two different Kubernetes types of objects. They're custom resources in Kubernetes. That's the plan for what it's going to build. And a controller, which is the thing that looks at the plan and builds what you tell it to. Operators manage a higher level of granularity in Kubernetes than simple controllers like stateful sets or deployments that you might be familiar with. Kubernetes operators allow you to install, update, and orchestrate containers based on your own syntax and your own needs. And there are tons of operators out there. There's a GitHub site, Awesome Operators, that updates every day that has new operators out there. But operators tend to fall into two categories. Those that create a job, and we're going to talk a lot about those today, and those that install or upgrade products and keep a product healthy. So I said all of these things, whether it's TensorFlow or PyTorch or Spark, all of these follow the same pattern. And the pattern is I build a job operator, I submit a YAML to that job operator, they spawn a bunch of containers on the node, they do the work, and then they finish. So they're in Kubeflow, there are a bunch of operators just for different types of deep learning workflows. So there's TensorFlow, PyTorch, Spark is separate, but it has its own operator. Katib, hyperparameter training, Chainer, MXNet, MPI message passing, Cafe2, and Pachyderm. Those are the ones that are in there today. There are more coming along every day. And the idea is that your data scientist picks one of these ways to write his deep learning job or his just statistical job, whatever he's trying to build. But he selects one of these operators, he creates some YAML, he fires it off, and that deploys all the containers in your environment. So just to kind of to highlight that again, You've got a kubectl client. You pass some YAML from it to Kubernetes. The controller is watching for that YAML. In this case, we're sending a TensorFlow job. The TensorFlow job controller sees that YAML. You've specified what the job should look like in that YAML, and so it starts launching containers in the environment for you. The containers are going to have your training code, if this is a training job, and it's going to create a generated model. It's going to talk to training data. In the TensorFlow world, there are three main types of containers: a master, workers, and parameter servers. Argo is a workflow operator. A lot of people use it within Kubeflow to build containers that actually run in later steps. Argo follows the same pattern. It has a YAML that's defined by Argo. It gets past the Argo controller, and the Argo controller launches a bunch of these containers. That's the pattern. It's a pretty simple pattern. Everybody does it. But it's really important to get that down in your head, that that's what's going to be happening. So each data scientist will want to run their own favorite training framework. Lisa likes PyTorch, Mary likes TensorFlow. Encourage that heterogeneity in your environment. It'll make your data scientists happy. Try to run the job operators in a single namespace in your cluster. What I mean is this: the operators themselves should live in their own namespace. You don't want to clutter, have every data scientist run his own operator. So that saves you on resources. But run the actual jobs in user or tenant namespaces. That way you lock down the resources that those tenants are using. It requires a lot of RBAC to make all of this work, but if you do that, it really makes your data science environments a lot better. Technique 2, schedule your pods smartly. Consider Spark. So the Kubernetes scheduler is amazing. You can schedule based on dozens of things. So we're putting all of these containers on all of these nodes. Kubernetes is pushing those out there based on a request. Well, these operators can use a number of tags and annotations and labels to make those pods live on the right nodes. If they need GPU, you need to annotate the pods that they need GPU. And so that's a lot of what you're doing, is you're trying to figure out what are the right annotations for my pods and what are the right annotations for my nodes. Spark, so I mentioned all of these follow the same basic pattern. Spark is probably the most advanced in thinking about all of these things. Spark goes beyond the basics today, even more than TensorFlow, in allowing many types of worker pod labeling, and even has a custom scheduler to launch pods based on HDFS fragments. So there are some really cool things these operators can do if they spend a little bit of time and energy in launching them in the right places. Technique number 4, avoid making data scientists hand-roll containers. This is probably my biggest pet peeve in the community today. One of the uglier patterns I see over and over is encouraging data scientists, all data scientists, to go in and build their own containers. Now, it's true, data scientists need to have whatever libraries they need. They need to build things the way they want them, but usually in most organizations, the pattern of the way things get built is very, very similar. So rather than encouraging a hand-rolled container type of pattern, the better idea is to create mount points in the pods, create standardized data science pods for training, and create mount points to pull in the things you need, like training data, training code, models, libraries, etc. And pull those in as volumes so that everybody's using similar containers, but they all may be using different code that's running inside of those containers. Spark leads the way with this. Spark has this notion of a resource staging server today. There's some debate about whether that thing lives on and how they may do it in the future, but Spark's really thinking about how to avoid this hand-rolled problem. So this is something that I expect TensorFlow and some of the other operators to kind of catch up with soon. Here's the Spark operator. Again, similar pattern. You send a Spark YAML. It looks a lot like a Spark submit. So if you've ever done a Spark submit, the YAML looks like a Spark submit. It gets sent to the Spark controller. The Spark controller launches a Spark driver, which is equivalent to TensorFlow master. That Spark driver talks to a custom scheduler that figures out where these workers should launch, the executors. The executors get launched on nodes, the right node to talk to the right HDFS instance. The resource staging server can push the training code into each of these executors, so you don't have to have a new container for each Spark job. And you get a generated Spark model at the end that you can use in streaming, et cetera. So technique number 4, separate your compute from storage. So you saw I launched a storage cluster. I also launched some Kubeflow stuff. You keep those things separate. You want to scale your compute jobs or your training jobs separately from storage, and that's something that's tricky when you don't have Kubernetes. Remember that you can do that in Kubernetes. Kubernetes operators, so I said they fall into 2 categories. The other category are product operators. A lot of the stuff that you'll be building will require support infrastructure. Things like Kafka, things like MySQL, Airflow, et cetera. All of those have operators that make it easy to install those products for the machine learning environments. We have our own operator that's what I do in my day job. But a lot of what these things are doing is you have lots of really complex types of containers, and you can't just put them all in one stateful set. So you need multiple stateful sets, things communicating. Take advantage of those types of operators if you can. Technique 5, when you have the complexity in your own environment, think about building your own operator. Operators are really good for handling hard tasks. There are alternatives. You can build Helm charts. You can build K-sonnet files. I would really recommend taking a look at operators because unlike the other solutions, operators allow you to handle the whole life cycle. They're not just about install and uninstall. You can do different things depending on upgrades, et cetera. Okay, so we've talked about training. Let's go back to the first exploration. Users need these data science containers. I'm actually running out of time, so I'm going to move kind of quickly. I may need to launch Jupyter, RStudio, Zeppelin, all of these different types of notebooks. Notebooks are a secret weapon. You'll want your data scientists to launch as many notebooks as they can. The notebook spawning problem is an issue. You need to figure out how you want to do that. That's something that you should spend some time and attention on early on, is how you want to spawn them. Jupyter Hub and Ambassador is one way. You can build your own, and there are reasons you might want to think about that. Other types of UIs you'll have to deploy. You have central dashboards, TensorBoard for like history of TensorFlow jobs, Spark history, models, workflows, et cetera. Ensure users can monitor their own job status. This is something I see people make the mistake over and over. They say, well, we're not going to make our data scientists have to pay attention to things that are running in Kubernetes. That's not their job. That's the Kubernetes administrator. No, not really. When these data scientists are launching really complex training jobs that require tons and tons of memory and run for a long time, they need to be able to see if everything's still okay. They need to be able to see when it's causing memory pressure at different places so they can scale the memory down or scale it up. You need to really provide insight for data scientists when you're building the environment for them. So I'm going to finish these slides, and then I'll go back to the demo. Models can be embedded or served by applications. Everybody always forgets after training, how are we going to use this model? So if you're going to be embedding it in an application, that's one thing. You need to put it in your application. But if you're going to expose it externally, and you're going to expose the model over time as you make changes to the model, you need to think about what kind of microservices infrastructure you're going to use for streaming that model. Within Kubeflow, there are a lot of different ways to do it. The coolest is Seldon Core. It allows you to create all kinds of different proxies to do A/B testing and multi-arm bandits, et cetera, with your models. It's really cool. But you also have TensorFlow serving. NVIDIA has the TensorRT inference server. There's batch predict. There's Spark streaming. But you need to be able to serve your models, and so you need to think about how you're going to do that. The final slide on techniques that I wanted to make sure everybody heard is how do you handle tricky things? So Yarn is a big deal in the data science world. We all have tons and tons of Yarn workloads. Our company has customers that have 1,000 node clusters of Yarn today. Is that going to go away? What do you do? Well, you have three options. Yarn doesn't play well with Kubernetes. That's just a simple fact. The first option you have is replace it. So do you have something in Kubernetes that with time and thought is easier to use and faster to use? You can replace it, maybe drill for Impala. So the next option you have, you don't want to throw everything away though. The next option you have is rebase that tool. Spark-on-Kubernetes is a really good case study in rebasing the technology on something a little more modern. Hive on Spark could be another way to do some of these big data workloads. The final is coexistence. So it's possible to run containers of running Yarn in Kubernetes. It's just really ugly. A Yarn container is basically a container that starts out empty and then starts filling itself up. So it's not locked down at container design time. So it's very different than most types of containers. But that works. And you can use it in very specific circumstances. It also may be a viable option to just keep running those Yarn clusters outside of Kubernetes. That also makes a lot of sense. But that's the end of the presentation. I did want to just show you guys that some of this stuff came up. Let's go. I did want to show you a Spark or a this is a TensorFlow job YAML. So if we're going to send a job to TensorFlow, this is what the YAML is. It says we're going to create one parameter server. These are the arguments to the container. This is the, where is it? Yeah, this is the image that it's going to use, the Docker image. These are the workers. There are their parameters. That's that image. And if I go and I go over here, let's see, and do kubectl apply -f. I'm pushing out that TensorFlow training job, and it created that. So if I go back, our Jupyter notebook container came up that we launched before. I'm going to go back and go back to the Kubeflow. Go to the TensorFlow dashboard, and here's our TensorFlow job that we just launched. It's got 40 replicas and one master image, or one parameter server like we specified. So it's very easy to launch this. You want to make sure you're launching it in the right namespace. That's the key to, that's one of the key points that I want to just emphasize as we're wrapping this up. But thank you very much. I appreciate all the support.